Swayam Prabha. Digital India. Educated India.
Hello and welcome to this another lecture of the course on control systems. So we will continue to look at the examples of electrical circuits and how this use of Laplace transform helps us in analyzing these circuits or determining the time domain response of these circuits, which could be voltages across certain elements or currents through certain elements. In general, we know that we have to solve differential equations in order to determine these variables, these unknown quantities of interest, but Laplace transform simplifies that process considerably in that you do not have to solve differential equations anymore, but rather just deal with some algebraic manipulations, right, solving equations of the form Ax is equal to b, which are just systems of linear equations really, and then you can read off the inverse Laplace transform from a given table, which again, to reiterate, after a bit of practice you will actually remember. Right? Even if you do not, you will always have a table of inverse Laplace transform ready at hand. So it really should not be much of a problem. So this process of solving differential equations has been kind of brought down or reduced to sort of like an algorithm, which we generally like, because whenever we have it in an algorithmic form we can codify it. We do not have to specifically solve this each time you change one variable here and there, or each time you swap the input with another one. So that is the beauty of this process. In the last lecture we saw the example of this particular circuit, right, and we saw how the application of KVL, by treating these circuit elements exactly as if they are just the same in their transform domain, right, and then treating them like impedances, we obtain these KVL equations. We also showed you how you can actually read off the coefficients of these unknown currents by just visual inspection. Okay, so it's really a very attractive and simple process, and then you can just apply something like Cramer's rule to solve for this in the transform domain. Thereafter, like here in this step, you can apply the inverse Laplace transform. Now we've of course used KVL here, Kirchhoff's voltage law, although I told you earlier that if the unknown quantity of your interest is basically a voltage, a node voltage, then you better apply Kirchhoff's current law to simplify the process. And you've already seen here, right, that you determine the current here directly, but then you had to multiply it by an S, right, which is why this S went off, in order to get the voltage. So you had to multiply the current with a suitable impedance in order to get the desired quantity of your interest, which is the voltage. On the other hand, if you had applied, for instance, say KCL, let me draw that same circuit again. Yeah, so this is an S, this is a 1, this is also a 1, this is an S, this is another S, this is basically the voltage you want to determine, V out of S, and this is your input voltage, which is V of S. Alright. So now if you want to apply KCL to this, you have to first identify the nodes. So generally what we do is we take a datum. So we take this to be one of the grounds. So basically this node and this node, they are the same node basically. So this entire thing is grounded. So what are the different nodes that we have then? Okay. So let's say this is node 1, this is node 2, and this is node 3. Right, you see that's all we need just 3 nodes here. Once we've demarcated these 3 nodes, we can write the node voltage equations in the following manner. How? So what is V1? For V1 you can directly read off, you do not really need to write any node equation, you know that V1 is at the potential V of S, which is the input. So the first equation I will write is V1 is equal to V of S, that is it, as simple as that, since you do not have a series impedance here, right. So you do not have to convert it to its equivalent current source like we had suggested earlier, it is like an ideal voltage source. So you just read off the node voltage at node 1 is nothing but the input voltage. Similarly, now if you want to write down, let us say the node equation, the current equation at node 2, what is this? This is the datum, so this is at the 0 voltage level, right. So what are the currents here? So you see, if you sum total the outgoing current at this node, that should be 0. So let us say the sum total of the current flowing out from here can flow out through this and through this branch. So what is the current flowing out through this branch? It is nothing but V2 minus V1 over 1, okay, plus V2 minus V3 over 1 plus V2 minus 0, yeah, that is this, over S is equal to 0. That is your second equation. There is no external current source pumping in current to this node, so therefore the right hand side is 0, or right hand side and left hand side is just a convention. Here it was the left hand side, the external sources were put in here, here we are just writing on the right hand side, really does not matter, right. Okay, what about the third node? What are the currents flowing out? So when you are considering the third node, you consider the directions of currents like so. So you basically have V3 minus V1 over S, yeah, that is this branch, then V3 minus 0 plus V3 minus 0 over S, that is this branch, plus V3 minus V2 over 1, V3 minus V2 over 1 again equal to 0, yeah, that is this, okay. Again, and this is a pattern, okay, if you begin to see the pattern here, it is very straightforward. Here also I put it to you that you do not need to really pay very careful attention into the polarities and all of these things and get caught up in them. All that you need to do is just focus on individual nodes, and just like we saw these entries at the diagonals and the off diagonals of this matrix, that is A, the unknown, the coefficient matrix in the system of linear equations, here also our unknowns are basically V1, V2 and V3. We have omitted the S, by the way, these are all in the transform domain. When I am writing capital letters, it means it is in the transform domain. So maybe I should also omit it here for consistency's sake, okay. You understand that this is all in the transform domain, yeah. So now if you carefully write this down, you will get the same result as what I would get if I just look at the pattern visually. What is the pattern? Look at V1. Of course for V1 there is nothing much to do, you just replicate the same equation here, right. So V is equal to V1, there is nothing really that you can do about this. For the second node, just look at this. So I have V1 times something plus V2 times something plus V3 times something is equal to 0 apparently. So what are these somethings? If you look at V2, which is the second node, second voltage, that is a diagonal entry in the matrix, remember. So what is V2? You see the sum of all the admittances, okay, the sum of all the admittances, these are dual methods I told you, remember. What is the admittances? Sum of all the admittances incident on this node V2. What are the admittances? If this is the impedance, then its reciprocal is the admittance, isn't it, yeah. So basically you will have 1 over S plus 1 over 1 plus 1 over 1, right. What about this, the coefficient of V1 in the equation for node 2? The admittance that is shared between node 1 and 2 with a negative sign. So I will put a negative sign here, and what is the admittance shared? It is 1 over 1. Why am I writing this 1 over 1? Because it is ultimately this 1 that is the impedance. So I am trying to write it as an admittance form, so it is 1 over 1. Similarly, what about the coefficient of V3? You see that the edge, this is called the edge, shortly it will be clear when I use some graph theoretic terms, the edge or the particular branch that is common, that is shared between node 2 and node 3 is exactly what will appear as the coefficient of voltage 3 in the equation for node 2, which is nothing but, again with a minus sign, 1 over 1. Now when I write the third equation, that is the simplification of this, I can just write it just by visual inspection. So I will just write V3 times something plus V2 times something plus V1 times something. What are these times? So let me look at V3. What is the sum of all the admittances incident on V3? 1 over S plus 1 over S. So it is 1 over S plus 1 over 1 plus 1 over S. That is it. What about V2? Whatever is common between V2 and V3, nodes 2 and 3, that is 1. So it is with a minus sign 1 over 1. What about V1? 1 by S is common between V1 and V3, so it is with a minus sign I will write 1 over S. That is it. So now again I have the same form, that is that Ax is equal to B. This time my x's are exactly the V1, V2, V3 vector. Yeah. So if I just solve for V3 directly from here, I will have my output. I do not need to multiply or divide this with anything unlike this case. Remember where I had to multiply this I2 by the suitable impedance. Okay. Here once I have solved for V3, because I know here from the way I have defined these node voltages that V out is nothing but V3. So if I have solved for V3 from these three equations, let me call this 1A, this is 2A, and this is 3A. Alright. So once I have solved for this system of equations given by 1A, 2A and 3A, right. So I leave it to you as an exercise to check that by solving for this you will get exactly, and you should, it is no surprise really, that you should get exactly the same expression for V out as you obtained using KVL. So it is a test that whether you apply KCL, KVL, if you know your basics, you will always get it right. Yeah. So this also again goes to show that irrespective of whether you use KCL or KVL, if you know how to apply those rules properly and if you know how to write those equations, if you can observe the pattern, right, then you should be able to do it fairly quickly and efficiently, as opposed to, for instance, say writing down differential equations to solve for each one of these, right. I am sure you would agree that this is a much more simple process, a much simpler process. Yeah. So hopefully that appears convincing to you. So at this point I should probably give you an exercise, but I will not leave you to think of the solution. This is a typical twin T circuit, okay, and this might look a little more complicated where you might wonder how you are going to apply this, this KCL or KVL or any of them, because this looks rather more complicated. So let me draw this. So this is the twin T circuit, for instance, and let us say here you have this R2, okay, yeah. So here you have this R1, there is also R1, right, and here you have a capacitor which is, let us call it C2, yeah, C2, okay, alright, and you have the voltage source here, the input voltage here, yeah, and this is where you have your load resistance, okay. So what you are basically required to find out is obtain current through RL. Now you might wonder how are you going to write down these equations. This is not a planar sort of a circuit, right, but this is where the abstraction helps, in the sense that this topology is nothing but the same as, I put it to you, the following topology. So I will first number these nodes and then you will see. So let us call this node 1, let us call this node 2. 2, let us call this node 3, and let us call this node 4, alright. Having done that, I would say that this, and let us call this the datum 0. So this is exactly the same as the following circuit. If you lay it out on a plane, if you lay it out flat on a plane, it is exactly the following. A little bit of observation would help you in figuring out that this is indeed so. So I am going to draw the so called equivalent graph for this, okay, right. So look, there are 4 nodes here, so I have just drawn them 1, 2, 3 and 4, and there is this 5th datum node, yeah, so which I am going to label as 0 here. So let me call this datum as a 0, alright, and let me just name them as 1, 2, 3 and 4, and now it becomes very simple. You see, what is the element connecting node 1 and 2? It is just R1, right, so just name this R1. What is the element connecting nodes 2 and 3? If you look at nodes 2 and 3 here, it is R1 again. Similarly, if you look at nodes 3 and 4, 3, that is this, and 4, it is basically C1. Again, if you look at nodes 1 and 4, which is basically this node 1 and 4, that is also C1, right. Now you have to look at all the nodes connecting to the datum. So between datum and 2 you have C2, so this is going to be C2. Between datum and 3, which is this node, you have RL, yeah. So this is the current that you are interested in obtaining, alright. Of course you can assign any arbitrary direction to this. Between datum and node 1, yeah, you have the voltage source, so this is where you have V in, right, you have the voltage source. And between datum and 4 you have R2. So now it is a simple matter to just assign some loop currents here, that there will be 4 loop currents, yeah, and once you found those 4 loop currents, you have given them suitable names, let us say I1, I2, I3 and I4, you just need to solve for I3 minus I2, that is exactly the current that is flowing through RL, right. So you have to solve for I3, you have to solve for I2 and just obtain the value of I3 minus I2. So solve for I3 minus I2 and you are done, right. So of course it is a little lengthier because there are more number of variables, 4 variables to be precise and 4 equations. So it is just a 4 by 4 system instead of the 3 by 3 that we had written out earlier, but you can easily observe, yeah, that this is exactly the same as solving for any other equation, even though this 20 circuit might appear much more complicated, and if you want to especially write down the differential equations for this and then solve, you will see that you will end up with a huge mess. On the other hand, if you are using the Laplace transform to solve for this system, things become a lot simpler and life becomes a lot easier, which is after all the purpose of this entire exercise. Alright, so hopefully we have seen how to use KVL and KCL effectively, yeah, in the transform domain to solve for currents and voltages of interest, right. So next, before we wind up with this discussion on circuits, as I promised to you, we will also talk a bit about solving for circuits when there are non-zero initial conditions, right, not just the zero state response, which is what basically all of these things give us, because we are assuming that the initial conditions are 0. So for instance, you might always encounter a circuit and you might be asked to solve for this circuit. So suppose there was a 10 volt source here, and there is this switch here. So at t is equal to 0, this switch is turned off, okay, it was on earlier. So let us say there is a 5 ohm resistance here, and there is another 5 ohm resistance here, and there is a 1 Henry inductor here, alright, and then okay, that is 5 ohms and that is 1 Henry, okay, and then there is another 5 ohm resistance here, and let us say there is a 0.1 farad, forget about how big that capacitance will be, it is just some value that we are sort of assigning to it. Yeah, so this is a switch. So now the question may be, well, to solve for ILT for t greater than 0. So what is basically being asked here is the following. You had this circuit which was having this switch turned on in its on position before t is equal to 0. So I leave it to you to check out, yeah, that at steady state, right, at steady state an inductor, when you have a DC supply, at steady state an inductor behaves like a short circuit and a capacitor behaves as an open circuit. Okay, so that is an additional exercise. Maybe you can just take an RL circuit like this and take this as 1 by S, this as SL, okay, and take this as I of S, alright. So you will see that I of S is nothing but V of S over R plus SL, which is nothing but 1 over S times R plus SL. So now if you want to find out IT limit t tending to infinity is equal to nothing but limit S tending to 0 S I of S, yeah. So you will see that this is going to be nothing but, this is going to be nothing but what? You multiply this S and then you let S tend to 0, this is going to be nothing but well 1 over R in this case, but that is because there is a unit step, right. So in general this is V by R. So basically at steady state, that is as t tends to infinity, the inductor behaves as a short circuit. Similarly you can check that a capacitive circuit, an RC circuit, it behaves as an open circuit at steady state. So with that knowledge in mind, we assume that before this switch was turned off, this circuit was already at steady state, which is to say that at t less than 0, the circuit was the following. Equivalent circuit was the following. Let me draw that. The equivalent circuit was, it's a 10 volt, right. So this is 5 ohms. Since the inductor is an open circuit, is a short circuit, sorry. So this will be the 5 ohm here, and the capacitor is an open circuit. Yeah, check that. Using the same technique here, like I used here, you will be able to find that the capacitor will be an open circuit. So what is going to be the current flowing through this? You will see that immediately that this current is basically 1 ampere downwards at steady state. This is okay at t less than 0. So before this switch was turned off, this is how the circuit was behaving. Now why is this useful? Because now you know from here that IL0 minus was exactly this current flowing in a downward direction, alright. So if you know that this circuit was the following, that current was flowing in a downward direction, now instead of just talking about the circuit equivalent from time domain and frequency domain, we will account for these non-zero initial conditions, alright. So how do we go about doing that? So here is how, alright. So let us take for example once again the 3 analogies. So let us say this is R in the time domain, this is I of t, okay. So in the frequency domain you can just replace this with R, this is I of S, that is it. It's terminal A, terminal B, terminal A, terminal B. Similarly, if you have, sorry, that will be an inductor. Similarly, if you have an inductor with a current flowing like this over across A and B, then remember, with non-zero initial conditions, you cannot just ignore the initial condition anymore, right. So, what is essentially your initial condition now? How is it going to behave? So, consider that S L I of S minus, okay, S L I of S minus I 0 minus is going to be the total voltage drop, yeah. This is going to be the total voltage drop across VAB, right. So, therefore, when you want to draw this analogy here, when you want to draw the analogous circuit here, you cannot ignore this unless this initial condition is 0. So, how do you go about trying to solve for this? Well, here's the answer to this. Okay. So, here's what we do. We take this, you see that these are of opposing polarities, right. So, you name this as A, let this current flow in this direction. So, this is I of S, let this inductor have exactly the same polarity as here, but now you have to account for this initial condition as well, right. So, how do you account for this initial condition? What about its polarity? Yeah, okay, I have missed out this L here for some reason, yeah, because it was L di dt, remember, yeah. So, this L should have been here. Now, recall that this is a negative sign, so this is going to oppose the polarity. So, this is going to be the minus sign, this is going to be the plus sign with L I L 0 minus, yeah. So, this is your analogy with non-zero initial conditions. Similarly, if you take the capacitor here, if you take this here, now what is going to be the initial condition? You see that I is given by C dV dt, that is the voltage drop across the capacitor. So, if you now want to write this out in the transform domain, you will have Is is equal to Cs times Vs minus C Vc 0 minus. In other words, if you want to replace this, right, you will have to add this. So, what is it? It means that Vc of S is equal to basically VAB is nothing but 1 by Cs times I of S plus 1 by plus 1 by S Vc 0 minus. This is a small v, by the way, even if it looks like a big V, all right. So, this is going to be the analogy. Now, you see that the polarities are the same, right, they get added on together. So, therefore, you replace this here with not just this capacitor here. So, you have to have this as well as a voltage source here whose polarity supports this, and the magnitude is nothing but Vc 0 minus over S, yeah. So, these are the equivalents, all right. Remember, very important, this is basically Is. So, remember that here, for instance, this IL 0 minus need not be flowing in the same direction as Is. So, if IL 0 minus is flowing in the same direction as Is, then this appears with a positive sign and the same polarity. On the other hand, if IL 0 minus were flowing in the different direction, then you will have to reverse this polarity, okay. So, this is with the assumption that of course, the IL 0 minus is flowing in the same direction. Similarly here also the assumption is that Vc0 minus had the same polarity as this induced by this flow of this current here for t greater than 0. If it is not so, then you will have to reverse the sign of this. So we will see that in this particular example itself right away, how this actually holds true, right. So here, now that we have seen this, let us focus on this circuit. What about the voltage, the Vc0? Vc0 minus, what about this? Now you see the entire voltage across this 5 ohm resistance is the same as this because there is no current flow through this. And what is this voltage drop? This is I times R, which is nothing but 5 volts, yeah. So now we can draw the equivalent circuit for t greater than 0. We have to totally ignore this part now, yeah, because this part is playing no more role in this. So we replace each of these elements with not just their equivalent frequency domain representations, that is SL and 1 by SC, but also with those initial conditions incorporated in the form of these sources, okay. Once we do that, this is how our circuit will look. Once again recall, we are going to ignore this part. In fact, this 5 ohm resistance can also be ignored, so we can completely ignore this part. We have to now just focus on this part, because when this part of the circuit has been switched off, it is only this part of the circuit that we need to be concerned with. So we redraw this circuit now. How? Okay, here's how. So of course the resistance comes with no baggage attached, so to say. Now the capacitor and the inductor, they have to account for their initial conditions as well. So this is the 5 ohm, alright, and this is the 1 Henry inductor. Suppose we are assuming a loop current in this direction, then this is the direction of current flow. So this is the polarity of the inductor. Remember, it is a passive element, so current flows from the positive terminal to the negative terminal, and this will oppose this, right, but that is only under the assumption that this is IL 0 minus times L. Now L is of course 1 here, so I could have ignored this L here, but let it be for the time being. Similarly, here we have this capacitor, so this is the polarity of this capacitor, but we will also have to account for this. What was this? This was 5 by S, right, because it was 5 volts, and remember you have to divide by S, Vc is not by S, right, so Vc not by S. And I do not have to bother about the sign here, because you see even prior to this switching, yeah, even prior to this switching, the polarity was exactly this. This was the positive terminal, this was the negative terminal of the capacitor. So the initial voltage had the same polarity as the polarity of the voltage as we have considered it to be in convention with this flow of current. On the other hand, this, now the polarity has changed. So this we have to actually write as minus 1. Why? Because this IL0, remember, was earlier flowing in the downward direction, as we have seen here, right, it was flowing in the downward direction, but now the current we have considered is flowing in the upward direction, right. So this polarity will hold so long as the initial current and the current that we have considered now in this loop flow in the same direction. Now it is flowing in the opposite direction, so it is minus 1, right. So now we can just sum total this and write it as a single loop equation. So what is the sum total of the voltage sources across this? You see, if you go from this minus plus plus minus, so it is minus 1 minus 5 by S on one side, that is the sum total of the voltages across the loop, and that is going to be balanced by 10 plus, what is the capacitor, 0.1. So I think it was 10 by S, 1 by 0.1 S is 10 by S plus S, yeah, this is going to be times I of S, alright. So in other words, we have to write minus of S plus 5 over S is equal to S squared plus 10S plus 10 over S times I of S. In other words, I of S is going to be nothing but, the S can cancel from both sides, minus of s plus 5 over s squared plus 10s plus 10. This minus sign just denotes that the actual flow of IT will be in the direction that is opposite to what we have considered here. So remember, because of our convention here, this became a minus 1. Why? To reiterate, this is very important. Remember the polarity of the current, the flow or direction of flow of current before the switching happened, it was in the downward direction, but we assumed that the flow of current is in the upward direction after the switching, right. So even though we considered the convention, we respected the convention here, yeah, according to this equation, plus minus minus plus, right, we have replaced it in the same fashion, but if this current were flowing in the same direction as IS, then this would have been respected, but since this current was flowing in the opposite direction, we had to account for it by a minus 1, yeah. So minus 1 plus 5 by s, plus of minus 5 by s of course, because this is a voltage rise and this is a voltage drop. So a voltage rise of minus 1 and a voltage drop of 5 by s, so it is minus 1 plus minus 5 by s, right. So I urge you to check that now. If you want to find out I of t, I leave that to you as an exercise. You can just take the Laplace transform of this, the inverse Laplace transform of this, and you will obtain your I of t. So that is how this circuit will behave. So you see that not only does Laplace transform help you in finding the transfer function or the zero state response, but it also helps you in solving for actual circuits when essentially you take off the input or you cut out the input and you see how the circuit comes to rest or decays, the variables decay, or the stable behavior of the circuit, right. So I hope that you see the versatility of this Laplace transform method that we just illustrated to you. With that we will draw to, of course there are a lot of example circuits that can be given to you as exercises and I urge you to solve for them, but with that we will put a close on this study of circuits. Of course we shall see other systems later on, like mechanical systems, which have analogies to these electrical circuits, and we shall be referring back to these developments that we have studied here very often, because as electrical engineers, as I said, circuits are things that we understand really well, okay. So now that we have seen how these circuits behave, comprising only passive elements, it is time to take a look at things like operational amplifiers, which are essentially active external sources, yeah, they involve some active external sources, only then can they act, right. So there are certain transfer functions which actually cannot be realized by just passive elements, okay. For them you need active elements, as a matter of fact. Those happen to be precisely some improper transfer functions, okay. So when you want to realize a practical differentiator circuit, for example, you generally tend to use these operational amplifiers. So it is important that we study operational amplifiers. The other motivation behind studying operational amplifiers is, of course, these days we have computers doing everything, but until a few decades back, which is maybe even before I was born, maybe some 50 years back, you had these analog computers, these huge analog computers. I happen to have been lucky enough to have experimented on some of these analog computers when I was an undergrad student. These days most people haven't probably seen them. So you have these analog computers which are built by these, using these op amps or operational amplifiers, bit by bit, block by block, okay, and you read off the voltage inputs to these operational amplifiers using some multimeters, right. So that gives you the initial voltage, and then you input some supply to it, and then you see how that integration action happens, yeah, or a differentiation action happens. So you realize these different transfer functions using operational amplifiers. So it is important, although these days we do not really use operational amplifiers in these applications, but as I said, even if they are not used for building analog computers, sometimes to realize circuits that allow you to design certain or synthesize certain controllers. So the practical implementation of a controller that you might have synthesized may be achieved using these operational amplifiers, okay. So it is important to understand how these operational amplifiers behave, and that is exactly going to be the goal of our next part of this lecture, okay. So we look at what operational amplifiers are. So in short they are called op amps. Okay. So these are essentially composed of two differential amplifiers. If you go through a course on maybe electronics, you might have encountered them already. If not, then you will soon encounter them at some stage, I hope, right. So symbolically here is how we represent an op amp. So an op amp has basically two input terminals. One is an inverting input terminal, the other is the non-inverting input terminal. So the one bearing a minus sign is basically the inverting end, the one bearing the plus sign is basically the non-inverting end. So this is basically the output end. So we call this V minus, the inverting input end, the V plus as the non-inverting input end. And as I said, this is an active element, so this requires external voltage sources of 5 volts. So this is VCC, okay. We will not get into the details of that. So you will have external voltage sources applied to these operational amplifiers for them to work. Now the idea is that V out is equal to some A times V in, where A is the gain, A is defined as the gain, and ideally A tends to infinity, alright. Also the second condition is that an operational amplifier has infinite input impedance. What that means is that if you have an operational amplifier here, it will not draw any current towards it. What is an infinite input impedance? An infinite impedance means it is basically an open circuit. So current cannot flow through an open circuit. So if you have an open circuit and you are attaching a source, a voltage source to it, then of course there will be no flow of current into that block because it is an open circuit, right. So an infinite impedance means that it will not draw any current towards itself. That is the idealization, alright. So the next idealization is it has 0 output impedance. So if it has 0 output impedance, it means it does not impede the flow of current out of it, okay. So everything essentially gets passed around this operational amplifier. So essentially what it means is whatever voltage you are inputting or giving as an input to the op amp gets reflected at the output terminal, because the entire current gets as if bypassed through the op amp, out through a bypass through outside the op amp, okay. Nothing gets drawn inside the op amp, right. So that is what these idealizations essentially mean. So let us do a little bit more formal study of this. So let us say this is V of D. So you know that V of D is nothing but V of plus minus V of minus, right. And then what is the input voltage? Now input voltage is nothing but this V of D. So this is, let us say, my first equation, this is my second equation, yeah, and of course this I can refer to as my third equation, alright. So in and of itself this is not very interesting, but now we shall see two modes in which an operational amplifier operates. So first we shall take a look at the inverting mode. The inverting mode, okay. Remember these idealizations, these will help us in deriving the input output relation for an inverting mode of operation, right. So how does this behave? Let me draw the op amp here. So this is the minus, this is the inverting end, this is the non-inverting end. So let us say you have an impedance Z1 connected here, and this is your input source V in, alright. This is of course the ground, and this is the non-inverting end which is also grounded. This is your output, alright. And here we have in the feedback path, we have another Z2, alright. Yeah. So now how does this work? Yeah. So let's quickly write down the node equations here. So this we call as our, let's say, what is the VD here for instance? So VD, recall from here, what is VD? VD is V plus minus V minus. So what is V plus? Since this terminal is grounded, this is nothing but 0. So this is 0 minus V minus, right. So if this is 0 minus V minus, that is our first equation. The second equation is of course V out is equal to A times VD. So recall that this is my VD, this arrowhead denoting the polarity, yeah. So this is my VD, alright. So this is going to be nothing but applying equation 1 here, this is my equation 2. So in other words, V out, now applying equation 1 and 2, I have this as minus A V minus. So it then turns out that if I can just evaluate the node voltage, this V minus, then I shall be able to get this relation. But even before that, you can now notice that this V minus, if I write it in this fashion as V out by minus A and let A tend to 0, right, then I am led to concluding that V minus also tends to 0, sorry, A tends to infinity, I am sorry, I am very sorry. So basically the ideal op amp is where the gain tends to infinity, not 0. So then I am led to concluding that this V minus also tends to 0, alright. But what does that essentially mean? It means as if this terminal and this terminal are shorted, it is like a virtual short, yeah, these are like, this is like a virtual short. So now I can write the Kirchhoff's current law. What is the Kirchhoff's current law? It is going to tell me that V in is the voltage at this terminal minus V minus, yeah, by Z1 is equal to the current flowing from V minus in this direction minus V out over Z2. But then I have already determined that this V minus is almost 0, no, it tends to 0. This is what KCL dictates. So I can now just use this here as 0, can I not? In that case, it turns out that V out over V in is nothing but minus 1 times Z2 over Z1. So now this is the beauty of it. How can I realize transfer functions? If I choose suitable Z2 and Z1, yeah, then I can use this operational amplifier to design suitable transfer functions, right. My freedom is unlimited, okay. So this is how this op amp or operational amplifier allows me to sort of synthesize circuit equivalents of transfer functions. So remember, so far we have seen circuits and we have derived their transfer functions. Now if you want to instead do the other way around, if you want to have a transfer function and realize its circuit equivalent or its operational amplifier equivalent design, then this is how you do it. Of course this is only one part of it, this is just the inverting mode. What if we look at the non-inverting mode of an op amp? So here is what we have then, the non-inverting mode. In the non-inverting mode, the connection is a bit different. What we have then is the following, we have minus plus once again as before, right, excuse me, and this time again we will have this inverting terminal, this is the non-inverting terminal, right. So it is connected to a voltage source which is plus minus V in, which is of course grounded, and this inverting end we have this Z1 and we have this Z2, alright. So this is the V out, this is the non-inverting mode of the operation of the operational amplifier, non-inverting mode operation, right. So now What can we say? Again we write V out is equal to A Vd, right. So this is our Vd, but what do we know about Vd? This is nothing but A times, you know what this terminal is now, this is nothing but, so V plus is equal to V in now, right, because that is the potential at the non-inverting end. What about the potential at the inverting end? So this is going to be now V plus minus V minus, but what do we know about V minus now? Yeah, what can we say about V minus? We'll get to that in a bit. For now, just observe that this V out, current through this is going to flow out like this, nothing is going to get inside the op amp because of infinite input impedance. Yeah, that is the basic premise, right, that is why we had those idealizations. So this is one branch of current which flows directly out through here. So if that is the case, then this voltage is being divided across Z1 and Z2. So what is indeed the voltage V minus? So V minus is nothing but this is a voltage divider circuit, right. So V out divided by Z1 plus Z2, that's basically going to be this current that's flowing out through here, yeah, and that multiplied by Z1 is going to be the voltage at this terminal, right. So now once again what do? We know that, so let us name this equation 1, name this equation 2. Now from 1 what do we get? We get that V plus minus V minus is equal to V out over A, as A tends to infinity, V plus tends to V minus. But what do we know about V plus? So we can then deduce that V plus is equal to V in, which will then be equal to, so this is one side and this is the other side, which is then going to be equal to V out into Z1 upon Z1 plus Z2, right. This comes from this and this comes from this. So putting these two pieces together, what we then have as a relation between V out and V in is as follows: V out over V in is nothing but Z1 plus Z2 upon Z1, which is nothing but 1 plus Z2 over Z1, okay. That is the relation in the non-inverting mode. So in the inverting mode we had minus Z2 over Z1, in the non-inverting mode you had 1 plus Z2 over Z1. An interesting observation, if you sum together the two, so because this is a linear system and you can use superposition principle, so if you are giving inputs at both, if you are giving the same input at both the inverting and the non-inverting terminals, you get an overall gain of 1. Yeah, this is the beauty of an op amp. So if you give the same input signal at both the input and the output terminal, you see that sum of the gain for the non-inverting mode and that for the inverting mode is equal to unity. Yeah, but all this is fine with, you know, what should I say, an idealization of the op amp. In reality, you know, nothing is actually ideal, right. So an actual op amp is a non-ideal system whose equivalent circuit is represented in the following manner, right. So here let me draw this non-ideal op amp. You will of course find a lot of problems with ideal op amps, mostly in your textbooks, but what if I made the op amp non-ideal and tried to find out the effect of those non-idealizations? So now I am putting an R in, which may be a very high value, but still it is not infinity, okay. So that is my R in, yeah, and this is going to be my V minus, okay, at this node. So this is of course grounded here, alright, and then let me say that here let me have a resistance at the inverting terminal and that is also grounded through this, yeah, and then I have a dependent source. So if you have done a course on circuit theory, you would know what a dependent source is, right. So I have a dependent source like this, which is basically nothing but A Vd, and remember Vd is nothing but V plus minus V minus, okay. And now instead of a 0 output impedance, I have some, albeit small, but some non-zero output impedance, okay. So this, of course my drawing will be rather bad here because I did not make out space for the op amp, but it will be an oblong kind of a shape, so excuse that. So basically now a non-ideal op amp would be something that looks like this. So let me draw this ground here so that I can accommodate the op amp and it does not look really ugly, okay. So these are all, assume them to be straight lines even if they do not look like straight lines, okay. So this is what is inside that triangle which denotes the op amp, okay, in a non-ideal case. So this is a non-ideal op amp and this is the V out, alright. So now if you want to write down the equations for this non-ideal op amp, you will have to bear all of this in mind. So what is my V out now? Of course I have to draw this line here. So for this op amp, for instance, this connection for instance, okay, so then you have, note that this V out is going to be nothing but this V minus, right, yeah, that is going to be our first equation, right. And then you have V in is going to be V plus, so that is going to be my second equation, right. So remember, because V minus is shorted with this output, right, so therefore it is going to be V minus is equal to V out, yeah, and V plus is just what is going in here. So this is your input that you are applying to this, right, so therefore you get this. So these are my first two equations, I can write straight away without any sort of that way circuit equations or so, and then I am going to write this. So now note that I am going to write this KCL here. So this is V plus minus V minus over R in. So what am I talking about here? It is this V plus minus V minus divided by R in. So it is this current that I am talking about now, right. And what is this current equal to indeed? So this current is nothing but equal to this V minus by R. So notice that this V minus is this, yeah, so V minus by R. So this is the current that is flowing out of here, right. So this is V minus divided by this R, right. So that is the first current I am talking about. In addition to that, what is the other current that is going to be this? So that is going to be this V out. Notice that this is the current I am talking about, that one I have marked in blue here. So this current coming in, maybe mark it through red here. So this is flowing out here. So this is KCL at this juncture I am applying. So V out minus, what is it? Is going to be A times, notice that at this juncture, yeah, it is a dependent voltage source which is basically characterizing this op amp. So it is A times Vd, and what is Vd? Notice this fundamental equation. So I am going to just replace this Vd with this V plus minus V minus here, right. And what is this impedance over here? It is R out. So R out is the impedance across these two terminals. So that is R out, okay. So that is my third equation. Now let me use a different color. So if I now substitute this here and this here, and also the same, by the same token, this V plus here and this V minus here. So I want to basically get everything in terms of V in and V out. So I want to eliminate this V plus and V minus. So I am writing it in one shot. So let me pull together all terms related to V out, and that will give me, if I am not mistaken, 1 by R, yeah, because V out is V minus. Notice, so VR 1 by R plus 1 by R O ut, okay, R out plus A by R out, yeah. So notice this is this V out by R out, that is this term, and then A by R out, that is this term, right, because this this term here, yeah. So though they are both minus and plus sign, so I am checking every sign as I go because I have this habit of making careless mistakes, not a good thing. So then I am also pulling this V minus to the other side. So again I have 1 by R in. Okay, so all V minus or V out related terms on one side and all V plus or V in related terms on the other side. That is generally how we find out transfer function or the transfer characteristics between two variables. On the other hand, I will only have this, you see V plus has only two terms related to it. One is this 1 by R in plus this A by R out. I hope I have accounted for every term now. How many are there? 1, 2, 3, 4, 5, 6. Here also I have 1, 2, 3, 4, 5, 6. Yeah, that is right. So this is my ultimate equation. Okay. So then based on this, what can I write this expression as? This V out over V in. Yeah, what is this gain? It is going to be nothing but 1 by R in plus A by R out divided by 1 by R plus 1 by R out plus A by R out plus what was it? Yeah, 1 by R in. 1 by R in. Please check with this. Yeah, it is just V out by V in. So this thing gets divided by this. Yeah. So now what I am going to say is this, you can take this up as an interesting exercise. You check that, look, this is a non-ideal op-amp. In the ideal case, we know that this A tending to infinity itself, we can divide this throughout by A. Yeah. So if we divide this throughout by A, then we will be left with this 1 by R out upon 1 by R out. So then we will have this going to unity. But now I am saying that in this non-ideal case, what you might as well try to do is take one of those parameters to be ideal and the other two to be non-ideal. So what do I know about the ideal case? About the ideal case, I know that A tends to infinity, R out tends to 0, R in tends to infinity. Now I am saying, already I have discussed what happens when A tends to infinity alone, even when R out is not 0 or R in is not infinite. We have seen that the gain is unity. So long as this op amp has infinite gain, it is good enough to act as an ideal op amp, irrespective of R in and R out. But now suppose the gain A is not infinite, but R in is infinite. Yeah. Then what happens? You see, then what will happen is this A by R out will remain, only this 1 by R in vanishes from here and 1 by R in vanishes from here. So what you have in the numerator is then A by R out, what you have in the denominator is 1 by R plus 1 by R out, yeah, plus A by R out. So that is not going to be equal to unity, right? The way you can make this go or tend to unity is if you have reasonably high values of A, maybe short of infinity, right? The other idealization is R out is equal to 0. So then you let A be finite, R in also be finite, but let R out go to 0. So of course in the way I have written this expression here, you cannot let R out tend to go to 0. So for that you have to probably rewrite this thing as, maybe let me write something as this. So this limit, whatever you have to apply, you apply there. So you write RO by A R in. So all the infinite terms, the terms that go to infinity in the ideal case, I am pulling them in the denominator. All the terms that are in the that tend to 0, that is this terms like R out, those I am keeping in the numerator. So then I will have R out upon A R plus 1 by A plus 1 plus R out by A R in. Yeah, now you are in a better position. So what I am saying is, turn by turn you first let R out tend to 0, yeah, then you let, so then you do not let this be 0. So at one time only consider one parameter to be idealized, the other two to be non-ideal. So first you consider R out to go to 0 and A and R in to be finite, yeah. So then you will see that this term vanishes and these two terms vanish. So you have 1 by 1 plus 1 by A, right. So the larger you make A, the closer you get to a unit gain, yeah, with R out equal to 0. Then you let us say consider R in tends to infinity. If R in tends to infinity, once again this term vanishes, this term vanishes, right, but you will be still left with 1 here, 1 by A here and R out by AR here, right, still a far cry from the ideal characteristics, which is unit gain, right. And of course the one thing that we have already discussed, that A tending to infinity. So instead of having all three of them be ideal, yeah, you consider only one of them to be ideal and the other two to be non-ideal, and just sort of as a trial check what happens in this case, right. So you will see that our goal is to get this to be unity, right. Let me use a different color. So goal to get, sorry, yeah, so goal is to get this to be unity, to get this to unity, and you see which one helps you the most there. You will see that this A going to infinity is one of the most crucial factors that helps you in getting there, right. So in case you get to this idealization, then you would have this op amp where you apply this V in here, yeah, and whatever you apply here at the terminal here, this is the non-inverting terminal, this is the inverting terminal, and as long as you have this shorted with the output here like this, V out, and this is the ideal op amp where of course we have whatever is applied at the input without any loading, it is transferred to the output. Later on when we discuss controllers and their realizations using these op amps, we will see more of these and the benefits of using these active elements such as op amps, okay. So in the subsequent lectures we shall now talk about something else. We have discussed enough, delved enough into electrical systems, maybe we will give you a few exercises in the next lecture, and then we will delve into mechanical systems and their modeling, okay. So till then, take care, thank you very much.